This is section 12.2, polynomial functions and adding and subtracting polynomials. So that's a fun word, polynomials. Spelled out like this, polynomials. So what a polynomial is, it's a set of terms adding and subtracting together. It's a specific type of expression. So we talked about algebraic expressions way back in the day, way back in, I believe it was chapter 1.8 maybe, or chapter 2. It was a while back. So algebraic expressions were things like this, where we would have like 2x plus y, or I could have, x minus 3, or I could even have x plus y plus z. All of these are algebraic expressions. I can add on to that by making exponents like we've been using. If I have 2x squared minus y to the third plus z, that's also an algebraic expression. I can even make it simpler, x squared minus 4. That's an algebraic expression as well. So all of these are expressions, and each one of these things right here is called a term. So that's a term right there. We talked about that ages ago. This is a term, that are each individual terms. So if I still have like a group of variables together, like 2x, y, z plus, I don't know, I can say 3x squared, y to the third, z cubed, each one of these whole entire things is considered a term. So a bunch of variables multiplying together make up a term with a coefficient in front or without a coefficient. It doesn't need to have a coefficient. Like for instance, that's a term. This is a term. And the number of terms in a sequence together make an expression, and they also make something called a polynomial. So we're going to talk about what the polynomial is and how to read what type of polynomial it is. First off, we have types of polynomials. It's a long word. Types of polynomials. First, we have monomials, which are terms that are just one group of terms together. Like I could say x is a monomial. I could say 2xy is a monomial. I could say y to the third, each one of these being separate different expressions. All of those are monomials. Whereas a binomial would be something if I add another term. So x plus 2, I could say 2xy minus, I could say minus 3. The other one, y to the third plus z. Notice each one of these right here, this is one term. One terms, or expressions with one term, are considered monomials. Expressions with two terms are considered binomials. If I have trinomial, the word has the word tri in it, T-R-I. Remember, mono means like one, bi means two, tri means three. So it should have three terms. I have x plus y plus z. I could have 2xy plus 3 plus z. Doesn't matter what order they're in. I could have x squared plus y squared plus z squared. All of these have three terms each. So each one makes a trinomial. Anything after that would be considered a polynomial if it has more than that amount. So let's kind of scoot all this up really quick, make room for it. Move all that up. If it's got more than three terms, we just call it a polynomial. So polynomials could be x plus y plus z plus a. Could even be 2x minus 3y plus 4z squared plus 5. All those are polynomials because they have more than three terms. Sometimes we'll generalize and we'll say all of these right here are polynomials. We just say what type of polynomial it is. But anything over 3 for trinomials makes it a polynomial. So remember this right here, these count the number of terms. You want to count all the terms in them. After that, we determine something called the degree of a polynomial. When we're talking about the degree, we're talking about what the exponent is. So let me go ahead and just use example 1 to show you some examples of degrees. Example 1 says find the degree of each one. All of these are going to be monomials. So for A, this one says 3x to the second power. To find the degree, what we want to do is we want to look at the exponents that are up here for each one of them. The exponent for the 3 right here is going to be a 1, right? This is going to be, we always write down this as a 1 in the exponent. And what we want to do is we want to look for the highest term out of all of them. So out of the 1 and the 2, the highest degree would be the 2. So we would say this is a degree of 2. If I have B, this one is negative 2 to the third x to the 5 power. So the degree is always going to be the sum of all the variables. So when we're talking about the degree, we usually want to pay attention to this. The number doesn't matter because on that one, that would have been just 3. So looking at the degree here, we don't care about the degree for this one. We want to look at this degree right here. So the highest degree out of all the variables is going to be this one right here. So this would be a degree of 5. If I make up another example that was similar to the other one, it doesn't matter if it's 3 to the third power x squared, we would still say that's a degree of 2. Even if this one's higher than that one, it doesn't matter because we don't want to look at the numbers. The number doesn't matter. What matters is only variables when we're trying to find out the degree. So let's look at C. C just says y. It's a monomial. It's only one term, so the highest exponent up there happens to be a 1. So it's a degree of 1. If we look at D, this one is 12x to the second yz to the third. This one has multiple variables. It has 1, 2, 3 variables here. Now remember in the last lesson when we talked about if you multiply two like variables, you add the exponents, right? You add the 2 and the 3 together. Well, we know we can't put all of these together, but notice when we added them together here, it makes a 5. So for something like this, this would be a degree of 5 if they all multiplied together. So hypothetically, if all of these bases multiply with each other, even though we can't combine them, we can still add up all the exponents to see what the degree would be. So 2 plus 1 plus 3 would make a total of 6. So this would be a degree of 6. And that's only if they're all multiplying together. And I'll do another example right here. Let's say we have 6x to the third, y to the second, z to the fourth power. Even though we can't put all of these together as in to one variable, we can in fact add up all the degrees. The degree of all those put together, 3 plus 2 is 5, plus 4 makes 9. It's a degree of 9. That's what it would be up together. If we look at E, this one just has the number 5. So remember, we don't care what the numbers are for the degree. However, we know that if I put a little variable right here, x to the 0 power, that would make 1, right? 5 times 1 ends up making 5, which makes that number right there. So the variable that's not written there has a degree of 0. So if there are no variables present, we would say it's a degree of 0. Now, what if we have multiple things inside the polynomial? We're going to find the degree for this next example. And we're also going to label the polynomial. We're going to label it as a monomial, as a binomial, or a trinomial. So A says negative 2t to the second power plus 3t plus 6. So we can do the degree or the name of the polynomial. We'll just do the degree first. So when we're looking for the degree, we want to look at each individual term and see what the degrees are for each individual term. Just like that last example, the degree for this term right here would be 2. The degree for this one would be 1. Degree for this one would be 0. So the final answer for this one would be a degree of 2. Here we don't add up all of these numbers because not all of them are multiplying together, so we wouldn't add, quote unquote, the exponents together. Over here we added all these up because they were all multiplying. So we added the 2, the 1, and the 3 that made 6. Here we added the 3, the 2, the 4 that made 9 because they were all multiplying together. Well, in this one they're not. They're addition in between. So what we want to do is every time there's an addition or subtraction symbol, it makes a different term. Each term has its own degree, and then we compare all of them and see which one's the highest one. Out of all of them, the 2 is the highest one. So then now we look at the polynomial. Since it has 3 terms, we would say it's a trinomial. So this is a trinomial. That's a degree of 2. If we look at B, this one says 15x minus 10. So if it's easier, you can do it the other way around. Is it a monomial, binomial, trinomial, or polynomial? Here, it's got 2 terms, so it would be a binomial. And then we want to look at the degree for each term. This one would be 1. This one would be 0, because the 1 right there is a degree, and here there is no, there's like an x of 0, so it would be x of 0 power. This would be a degree of 1, because we want to look for the highest out of these two. So the highest out of those two is the 1. For C, 7x plus 3x squared plus 2x squared minus 1. Again, let's see how many terms it has. It has 1, 2, 3, 4 terms. So it's not a monomial, it's not a binomial, it's not a trinomial. It would be a polynomial. Then compare all the degrees. This is a degree of 1. This is a degree of 2. This is a degree of 2. This is a degree of 0. Even though that these two are tied, it doesn't matter. You're still just looking for the highest one. So this is a polynomial with a degree of 2. Let me try like a little harder example that kind of illustrates everything we just learned. What if I have negative 2xy plus 4x squared y minus 8xy to the third plus, you can say, x third y to the second. Well, let's look at it first. It has 1, 2, 3, 4 terms, so it's not a monomial, it's not a binomial, it's not a trinomial. It would be a polynomial. And we have to look at the degree for each one. This one is a degree of 2 because remember 1 plus 1 makes 2. This one's a degree of 3 because it's 2 plus 1 makes 3. This one's a degree of 4 because 1 plus 3 makes 4. And then the last one would be a degree of 5. Now compare all of those degrees, and 5 is our highest. So we would say degree of 5. So each set of polynomials has a different type of polynomial and a different degree for each one. And knowing the degree and what type of degree it is, it's really important when you go into college algebra. It makes it a bit easier to find, or actually makes it a lot easier to find out the shapes of graphs. You learn that odd numbered polynomials in one variable will rise and fall on different sides. If it's an even number with one variable, exponents might rise on both sides, fall on both sides, but this degree affects the graph and the number of terms affects the graph as well. Let's look at example 3, and we're going to do the same thing. Find degree and polynomial type. This one is 7x squared minus 6xy plus x squared minus 3y plus 7. Well, we already see more than 3 terms, so this would be a polynomial. And the degree, look at all the individual ones, this would be a degree of 2 from that. This would be a degree of 2. This is a degree of 2. That's a degree of 1. Nothing here, so that'd be a degree of 0. Highest is 2, so you would say a degree of 2. And that's how we would define it. Now let's go ahead and look at function types and defining polynomials. This is example 4. Going to get into functions a little bit. Now that word function isn't going to be introduced till later on in your next class, but we're kind of talking about it here. It says if px is equal to 3x squared minus 2x minus 5, it wants us to find the following. Okay, so first off, this right here, if I say px, p parentheses x, this parentheses right here next to it, we read it as a word of. So I say this is p of x. That's how I read it. It would be p of x. If I had something else, like later on you're going to learn different things, like f of x, we would read that as f of x. It is not p times x. You don't say like capital P, p times x. That would be incorrect. That is not what we want to say for this. We want to say p of x. So for this bottom one, f times x is not correct. We do not want to say f times x. We would say f of x. Now this function notation is useful. For instance, let's look at a. It wants us to find and substitute 1. So it wants us to basically find p of 1. So p of 1. Essentially what it wants us to do for this function at the top, I'll go ahead and rewrite it down here. P of x is equal to 3x squared minus 2x minus 5. It wants us, instead of writing x here, we're going to write a 1. And what we're going to do is, all the x's we see right here, 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 we're going to put a 1 instead in place of all of them. So we're going to substitute them all into there. Just like we did way back in chapter 1.8 when we were just substituting them in. So p of 1 is equal to 3 parentheses 1 squared minus 2 times 1 minus 5. Notice I substituted a 1 in for all of the x's. So what was here, here, and here, we replaced with 1s. So what you want to do is simplify this side now. This would be 3 parentheses 1 squared is 1. You have to do your PEMDAS. We can do multiplication. Negative 2 times 1 is minus 2, and rewrite the minus 5. PEMDAS says we have to do this first. 3 minus 2 minus 5, and then simplify all that. 3 minus 2 minus 5 would make 1 minus 5, and that makes negative 4. So ultimately our answer is p of 1 is equal to negative 4. What this tells us This function notation tells me whenever I plug the number 1 in for the p function, I get -4 as my answer. This is useful for like a business model or some kind of graph you may be reading, meaning, oh, what are my profits when I sell, maybe one item? Oh, well, I lose $4 when I sell one item. That could be the idea. You might need to produce more because it's too expensive to produce just one item. You might want to produce 100 because it doesn't really cost that much to create 100 versus one because you have to set up everything, buy a lot of supplies. They can only buy the supplies in bulk to make this item. But it tells us something. We can just read it. We read it as the profit for one item is -$4. That's not what this function is for, but it could be something like that. And then you can make a table of values. You could say, hey, for every x value, remember this from chapter 10, I get some kind of p of x value. So when I plug in 1, I get -4 as my answer. So let's try b for the same problem. I'm going to go ahead and copy all this, and we're going to take it to the next page. Copy and paste. It wants us to find, for b, just a different value. For b, it wants us to substitute -2. So p of -2. Remember, our function is p of x is equal to 3x squared minus 2x minus 5. So instead of x, we're going to plug in -2 for all of the x's. So every x that we had here, we're going to substitute with a -2 instead. Then go ahead and simplify this right side. -2 squared makes 4. 3 times 4. -2 times -2 makes +4. Minus 5. 3 times 4 is 12 plus 4 minus 5. 12 plus 4 is 16 minus 5. 16 minus 5 is 11. So when I plug in -2, I get 11. Now, clearly this wouldn't make sense in terms of a profit equation, right? We can't plug or make -2 units and make $11. So this function can represent anything. It might be something in particular, but it's still an equation. So we can make a table of values. For that last problem, when we had 1, we got -4. For this problem, we plugged in -2, we got 11. We get a table of values. The reason why we use this function notation is just because I can see right here what I plugged in to get this answer right here. That's why we use this kind of function notation. You're going to be seeing it all the time in your next class. So what we plug in, we get a result. So it's really something called an input and an output. So you could have input and outputs for a lot of real life situations, right? The more maybe we run, like if we run outside, we do a lot of cardio, the more we run, the lower our heartbeat will be, right? Our resting heart rate will decrease because our heart gets healthier. Or something like maybe the more we eat, if I don't exercise, the more I eat, probably going to gain more weight. So the less I eat, the less weight I gain, or I might even lose weight. There's all these different function values. A lot of little hypotheticals. The faster you drive, the sooner you'll get to a place. The slower you drive, the slower you'll get to the place. Some kind of input results in some kind of output. The more you study, the more likely you're going to do better on the test, right? So the more you study, the higher the grade. The less you study, the lower the grade. That's the idea, but of course that's not always true if you just happen to get stuff right away. But those are functions, this input and output sense. So now let's get over to simplifying these polynomials. Let's look at example 7. Oh, sorry, this is example 6. What's this to simplify? By combining like terms. Let's look at A. We've done something like this, -3x plus 7x. Because these two have the same exact variable right there, we can combine those two to make negative 3 plus 7 makes 4x. We can combine those two. For b, x plus 3x squared. Here, on the other hand, we need to make sure this whole thing and this whole thing are the same. On a, x and x are the same. But on b, x and x squared are not the same. It doesn't matter if this and this are the same. The entire base and the exponent have to match. This exponent up here is a 1. So because the exponent is a 1 and not a 2, or vice versa, this isn't a 2 or a 1, we can't combine them together. So for b, we would just say that it's already simplified, or we cannot combine. So already simplified, or we cannot simplify it. This one would be your final answer. Can't do anything with it. For c, 9x to the third plus x to the third. Here it's different. X to the third and x to the third are the same. Just like this one, x and x are the same. If they're adding, we put the numbers together, right? We put negative 3 plus 7 makes positive 4. And we did that as long as the variables are the same. So for this one, since x to the third is on both of them, we can go ahead and combine. This and this are the same, so we can combine the front numbers. 9 plus 1 would make 10. So this would end up making 10x to the third. That's our answer, because 9 plus 1 is 10. And we can only do that because these two are the same. They have to be entirely the same. D, 11x squared plus 5 plus 2x squared minus 7. Go ahead and erase some of these marks. It's from my hand. Now, this is a big old one, a long problem. We need to look for like terms in the entire polynomial. So if I look here, I want to look for other x squareds, and I see another x squared here. So what I like to do, and I showed you all this before, is underline the like terms. Then I look for the numbers. Oh, is there another number I can combine? There is another number I can combine. So since x squareds go with x squareds, and numbers go with numbers, we can combine those two in one step. So 11 plus 2 makes 13x squared. 5 minus 7 would then make negative 2. And that would be your simplified polynomial. So we can combine all of the like terms for those because they have the same variables. Let's look at example 7. It's going to be the same exact idea. Combine like terms, so simplify. Negative 9x squared plus 3xy minus 5y squared plus 7yx. This one's a little tricky, looks a little different, but don't let that bother you just yet. First off, before I want to combine any of these, I want to make sure everything's kind of like in order. Notice this is right here in XY order. This one's in YX order. I like to kind of organize all of my expressions to be continuous or have continuity, meaning they look the same. So y and x, remember, because of the commutative property, it doesn't matter what the order I write them in is. I'm going to write them as 7xy. Now everything looks a little bit more continuous. There's some kind of continuity. It all looks in order. Now what I want to do when I'm looking for like terms is examine everything. Are there any other x squareds? I don't see an x squared here, nor here, nor here. So if I have nothing to combine, I'm just going to go ahead and rewrite it. So this is equal to negative 9x squared. If I want, I can cross this out so I can visually see I'm done with it. And I've already copied it over here. Helps you do step by step. Next one, I need to look for another term that has an x and a y. Only an x and a y. I'll show you another example on where they could be a little different. So that one, x and a y, I find an x and a y right here. If I combine the 3 plus the 7, that would make 10. Plus 10xy. I can cross them out if I want to visually get them out of my field of vision. This way I don't have to look at them anymore. Then y squared. Are there any other y squareds? Well, I've crossed everything out, so there's no other terms to combine. So this would just be negative 5y squared. And that would be your answer. So let's look at I'm going to make up a different example. Say I have 2xy minus 4x squared y plus 2xy squared minus 4xy, I'll say plus 6x squared y. This one looks a little confusing, but we need to examine everything piece by piece. I like to work left to right, like go this direction when simplifying things, and then I can organize them later. Let's see if we see any other xy's. Now, all of them have some kind of xy component, but remember, they have to be exactly x to the 1 power, y to the 1 power. So they have to say just xy. So I'm looking xy. Is there any other xy? This right here is not. It has a square right there. So that's not it. This neither. Right here. That has x and y exactly. So 2 minus 4 would make negative 2. So this makes negative 2xy. I'm going to cross those out now to get them out of my field of vision. And let's move on to the next one. Are there any other x squared y's? Meaning it has to have x squared and y exactly. They have to be the same exact thing. This is not. That's the other way around. That has x to the 1 power and y squared. So this one would not work. So keep examining. I can skip this one because we already did it. Oh, this one. X squared y. They both have the same exact variables. So we can combine those two and underline them. Negative 4 plus 6. That makes plus 2x squared y. Get them out of my field of vision because we already combined them. The last term is this. Nothing to combine it with. We can just rewrite it. So paying attention to detail is important. This would be your final answer. I could even have something with just a bunch of different variables, but they have to be the exact same. If I say 4xy plus 5xz plus 6, we'll say yz minus 10xz plus 7xy. Have to examine each one individually, and it works better going left to right. Are there any other ones that say xy? Here's another one right here that says xy. 4 plus 7 makes 11xy. Cross those out. Let's keep going. Are there any other ones that say xz? Oh, here's another one that says xz. 5 minus 10 makes negative 5xz. Cross those out. And you can see we're left with yz, and there aren't any other yz's. So we're just going to put plus 6yz. And that's your final answer for that one. All right, so let's go ahead and move on to something a bit more complex. Now that we know how to simplify giant polynomials and condense them, What we're going to be doing now is combining polynomial with a polynomial. So example 9, it says to add. Sometimes you'll just hear people say simplify. A says 7x to the third y minus xy to the third plus 11 plus 6x third y minus 4. It's a lot of stuff. Okay, so let's break this down. First off, if there's a plus sign and a parentheses right there, remember the associative property a long time ago said as long as everything here is adding and subtracting, everything here is adding and subtracting, the order of which we add and subtract them doesn't matter. So what I can do is I can just drop all of the parentheses. So this would be 7x third y minus xy third plus 11. And I'm just going to rewrite all of this. Plus 6x third y minus 4. We're back to square one, just like we did on the other problem. Let's examine from left to right. Are there any other, still zoomed out, fit tight. Are there any other x to the third y's? Got another one right here. 7 plus 6 makes 13x cubed y. Get them out of your field of vision. Let's go to the next one. This one is different. It's xy to the third. There's no other xy to the thirds, so we can just write minus xy to the third. Get that out. Finally, 11 minus 4, that makes 7. And there you have it. All simplified into one polynomial. So we added two separate polynomials together. If I do b, the next one, 3a to the third minus b plus 2a minus 5 plus a plus b plus 5. Again, as long as there's an addition between all of them, and there's no number in front of here to distribute, nor any number in front of here to distribute, we'll get to that in the next section. We can drop the parentheses. 3a to the third minus b plus 2a minus 5 plus a plus b plus 5. Examine left to right. Are there any other a to the thirds? And I don't see any exponents listed anywhere here, so there aren't any other ones. This would be 3a to the third. Let's move on to b's. Do a different color. Got a b here. Any other b's? We got one right there. Negative b plus b, that makes 0. So those end up canceling out. We don't need to write anything down. Let's look at a. I got another a here. No other a's. So positive 2a plus 1 makes 3a plus 3a. Lastly, we got negative 5 plus 5. Those are opposites, so those also cancel out. This is our answer. Remember, we cannot combine those two because they have different exponent values. So 3a to the third plus 3a would be our answer. So whenever you're adding them together, it's easy to just add them horizontally like that. Now, let's try example 11. It's just subtraction. It says to subtract. But, I'm just going to put simplify in parentheses because they mean the same thing. Like, it's telling you to subtract, but later on, the instructions aren't going to tell you to subtract. You just have to know that you have to simplify it. This one says 2x to the third plus 8x squared minus 6x minus 2x to the third minus x squared plus 1. Now, we worked with something like this when we were talking about the distributive property. Here, we can't just drop all of the parentheses. We have to worry about this right here. Whenever it's a plus sign, all of this stays the same when it's a plus sign. But when it's a minus sign, remember this is like a -1, we have to distribute that negative to everything on the other side. So essentially all the signs will change. The left one, however, this one, is going to stay the same. 2x to the third plus 8x squared minus 6x. Distribute that negative to everything on the right side becomes minus 2x to the third plus x squared minus 1. That's the only extra step you got to do. All of these signs right here are going to end up changing. Now we're back again to what we were just working on. Let's look for x cubes. Got an x cube here, and they happen to be the same thing, -2 and 2. They're opposites. So we can just cross them out. Let's go over to x squared. I got an x squared here, and I got an x squared here. 8 and 1. Those combine and make 9. So it'd be 9x squared. Cross them out, get them out of my field of vision. Looking at x, I don't see any other x's, so that's just going to become -6x. And then you can see here there's no other numbers to combine, so it'd just be -1. And that's simplified. So let's try example 13. And I'm going to do letter B. And it's just going to say simplify. So B has 9a squared b squared plus 6ab minus 3ab squared minus, might have to write this a little smaller. Let me go ahead and write it a little smaller because it's a lot of stuff. Here's letter B. 9a squared b squared plus 6ab minus 3ab squared minus 5b squared a plus 2ab minus 3 minus 9b squared. All right, so let's get the minus sign again. Remember, we want to distribute that negative to everything on the right side. So take this negative, you got to distribute here, 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 and here. There's 4 things we have to distribute it to. Left side is going to stay the same. 9a squared b squared plus 6ab minus 3ab squared minus 5b squared a minus 2ab plus 3 plus 9b squared. A lot of stuff going on. But now we get to finally simplify, narrow it all down. We want to look for anything that has a squared and a b squared. Look in, the second one doesn't, and it doesn't look like any of them do. This, none of them have a squared, b squared. So I'm just going to write down 9a squared, b squared, cross it out. 6ab, we want other ab's, and we have another ab right here. So 6 minus 2 makes 4. So that's going to make plus 4ab. Move on to the next one. ab squared. Now, it doesn't look like there's one in that order, but if you look here, that one, if we swapped them, that would be 5ab squared. So we could actually put those two together. These two could be together. So it's -3 minus 5. That makes -8. I'm going to kind of clean this up so we can see. Oops. There we go. So that makes -8ab squared. And I put it in ab squared format. No other numbers and no other b squareds, because you can just see these are the last two and they don't combine. We can just rewrite them. Plus 3 plus 9b squared. This would be your final answer. It looks ugly, but that would be your final answer because nothing combines in there. Sometimes we'll make it a little nicer by putting it in descending degree order, meaning like If we go back to naming the degrees, this would be a 4, this would be a 2, this would be a 3, this would be 0, and this would be a 2. Sometimes we put them in descending degrees, so 9a squared b squared minus 8ab squared plus 4ab plus 9b squared plus 3. Essentially just reordered everything according to the commutative property. You don't have to do it, but this is in descending degree order. And it just looks a little cleaner. And some math books will have the answers like that because it's neater and we can see them in descending degree order. Right. So that would be adding and subtracting polynomials. The homework might ask you to add and subtract vertically with the polynomials, and you could check out the book on that. Personally, I find it more confusing, and adding horizontally like we did here and here is how you're going to do a lot of your math anyway, especially when you go to calculus and everything. A lot of people will just underline and find all the common variables instead of adding them vertically and horizontally. I think it makes it a bit more confusing and takes up more paper. This is going to be the classic approach. So go ahead and look at it if you're curious, but if the homework asks you to add it horizontally or vertically, don't worry about it. It doesn't know if you did it horizontally or vertically. Just simplify it however you feel. And again, I feel like this way is the easier way. And that's 12.2. Go ahead and head on to 12.3.